Hey everybody, I posted the top hat question for the beginning class. It's 10:20, so let's get started. Since I was away for a conference, I just want to get a feel as to how we're doing in regards to one of the critical topics of the diffusion module. And also, we'll probably be using this concept later on in your life, so we should get it squared away before we move on, if you're not already using it. All right, so as you're trickling in, there's a top hat question that is open. I'll wait for a few more folks to put in the answer so that I can gauge how much time today to devote to Fick second law. Okay, I'll still keep it open but see what the responses are so far. Okay, so the majority of you is not that comfortable for a number of reasons, I imagine. One, if it's your first time seeing it, we've only discussed it in one lecture so far, and I think you've only really had one practice problem in class, but it does come up in your homework, and it will come up in many instances in your life. So I think given your response, it's good that we go over that in greater detail today. But before I do that, my guess is you probably will want to discuss the exam in some detail. So here is some statistics. I'm giving you these numbers as is. There's no connotation behind this. There's no projection of how well you're going to do. These are just numbers so that you know some information about the exam, and then you can conclude for yourself how best to proceed with your own studies. Also, I'm not comparing these numbers or say anything about them relative to previous exam one, mainly because it's going to be apples and oranges. This is a new format for this class and for the department as a whole. So to compare it with how we've executed exams in the past would not be on par. So as you know, you had 18 questions, 5 points each. So your total score, raw score, was 90 points. This distribution does not take into account the overwhelming number of you that have taken the past exam. So of course you would add on 5 points. So these averages might adjust. The score might adjust a little bit, and the average will move a little bit slightly because everybody will be bumped up just a little bit, right? Because you would have gotten your free, quote unquote, 5 points. Obviously you did some work for it, so it's not absolutely free, but it is easier to obtain than the exam. Let's see, what else did I want to say about that? So we're gathering statistics as well on your experience with the digital exam version, to see if we will proceed with that throughout the course and also throughout for the future of this type of large lecture course, I've talked with Proctorio, and it appears that there were 6 restarts that were necessary due to whatever technical glitch was communicated to Proctorio, and they have reported that they've responded to all these requests within 6 seconds. So I don't think, from a time perspective, I don't think it was a major disruption if you had some technical glitch, but please let us know and communicate with us if it were a bigger deal than how we're interpreting it. But for the most part, the overwhelming majority of you did not experience any glitches and seemingly went well as it could have, given that it is an initial rollout, okay? Now, also, there is a small minority of you that have not uploaded your note sheet within the 24-hour time period that was required of you after the exam closed. Now, for the first exam, we've not enforced or had a policy on penalty because we sort of anticipated that you would be overwhelmed with completing your exam on a Friday at 5, and you sort of pieced out for the weekend and totally forgot to upload. We'll send out reminders in the future because for exam 2, there will be a penalty if you don't upload within the permitted time frame. We understand the exams are very draining and they can take a lot out of you, and the last thing on your mind is to upload something. So given that there's no penalty for exam 1, but please do so. If you're one of those individuals who will have already received an email from me sending you a friendly reminder to do so. Okay, and then your TAs will continue to nag you until you fill out that form. Okay, but that will not be the case for exam 2. And of course, exam 2 will be the same. We'll have a guide and resources page so that everything will be spelled out clearly. If the format changes at all, we don't anticipate it to, so look out for that when the time comes. Any questions specific to exam 1? Yes.
Will you post the
Yes. Yes, the solutions will be posted. Your TAs will dedicate time to go through that in class. Of course, you still have a worksheet for this week to give you an opportunity to practice the larger points that we would like for you to really know well. So once again, as a class, you can decide how much time to devote to reviewing the exam or going over the homework or working on the worksheet as your recitation needs. Okay, but your TA will be devoting some time to that so that all your questions will be answered. And we haven't released the answers yet, given that we want to make sure that everybody takes their exam before that gets released. Yes. Yeah, I just didn't add 5 because, you already know that, right? You can bump it. I mean, it's already in Carmen. This is just to report the class average, which you might not necessarily have all the information to, just to give you a sense of how inverse this log normal is. In general, even though I said apples and oranges, I don't want to compare just because the way we administer the exam is different. The topics, the order of topics is also different. So it's really impossible to compare. However, exam 1 typically has come in at about 75% average with some sort of reasonable Gaussian distribution, just because the law of large numbers is on my side, right? So there's no curving. You all work yourself out, given that there's typically enough students that there's no curving that's needed. Although there's plenty of curving that's already built into this class as it is. Okay, now we're going to move on. We'll also come back to some slip planes because I realized we may have rushed through that a little bit. So I want to go back after we finish diffusion, go back to strengthening and deformations module. So I just want to note some concepts and emphasize some concepts on slip planes and slip directions. But I also want to complete this module in a reasonable period of time. So let's see, I'm going to duplicate my display. So I'm not going to belabor the point and go through what Janet has already talked about when she covered my lecture last week. So I'm just going to go over the highlights, and then we'll do some practice problems together and manipulate the solution to Fick's second law as well as Fick's first law by solving a set of equations. Okay, so I hope it's pretty abundantly clear that diffusion is basically in everything, in all materials processes that you will encounter as whatever engineer that you are or will become or change into. Okay. Clearly, bio applications are, well, there's a lot to say about breathalyzers and how accurate they are, but certainly that's a chemical process in terms of diffusion of molecules, right? Diffusion of gas molecules as well is extremely important for everything that we do, because we compress gas and also we release gas in outside, and that could have a major impact for you if, let's say, you're parked next to a building that has a lot of nitrogen from the liquid nitrogen dewars that are outside, right? All that nitrogen that's coming out, if you park your bicycle that has, let's say, a metal frame for a long period of time, what do you think will happen when that metal comes in contact with all that nitrogen that's coming out? Or hydrogen for that matter. If you have a compressed tank of hydrogen, think about fuel cell application, renewable energy, all these things that are coming online, right? You can buy a fuel cell car these days. All these things are coming online. You really need to think about, has a company thought about their diffusion mechanisms? Most likely, yes, right? Because how else are they going to have a safe product that will pass all these safety standards? But gas storage is a huge area where diffusion plays a key role, right? So if you're storing hydrogen, you're going to want to contain the hydrogen, but it's a small molecule, it diffuses very quickly. And so over time, if you have a compressed tank of hydrogen, it's going to embrittle the material, the metal casing, the tank itself, right? So solving how long you have, and if your material is going to hold up to hydrogen embrittlement is key. And of course, this has applications in the nuclear industry as well, because you're trying to contain all of these quite toxic and diffusive species. And so if you store it in some sort of tank and then you bury it underground, who's to say that it's not going to leak outside and then cause a number of issues? So these are all the things that we concern ourselves with as material scientists when we think about controlling diffusion processes. Now, nitrogen embrittlement is also a huge issue. Back to the bicycle example. So I would think twice if I were you, if you happen to see a nitrogen dewar. Now that nitrogen is obviously going everywhere in all directions, but if you were in a closed, confined space, I would think twice about that. And what's coming online is lithium-ion solid electrolytes. As you know, the current technologies that we have right now are used mostly for mobile devices, rechargeable mobile devices, mostly use lithium-ion technology that have liquid electrolytes in them. And so electrolytes are just salt in some sort of solvent, right? So the salt is typically something like lithium hexafluorophosphate, so that's LiPF6. It's usually in a carbonate-based electrolyte. It's quite corrosive. Actually, and over time, the stainless steel can actually become brittle and corrode. That's not for a long time though, but that's not actually not your big problem. Your big problem is that you're using liquid electrolytes as it is. And so when batteries catch on fire, that's due to thermal runaway. And before you even get to thermal runaway, it's all because your material selection from day one was a liquid electrolyte so that you can move these ions very quickly from one electrode to the other, whether you're charging your phone or you're discharging so that you can use your phone. Okay, so material selection from day one has already predicted how this battery is going to fail, how this material is going to fail, and eventually catch on fire in your pants, right? So those are like the videos that we've seen with the Samsung S7 a few years ago. I think some of you still may have been in high school, maybe if you're on the younger side. that all could have been prevented if we had just used solid electrolyte. These are ceramic type materials, these are polymer type materials, but mimicking ion diffusion in the solid state versus the liquid state is no small task, right? So diffusion plays a huge role. How we understand ions moving through a lattice directly influences how we select materials and how we engineer materials so that we basically have a paradigm shift when it comes to energy storage as a whole. And why do people care? Well, people care because it's a like multi-billion-dollar industry for the Apples of the world, for the Teslas of the world, and probably for electrification of potentially, you know, aircraft as well. So of course the military has huge, you know, investment into looking at these type of technology. Okay, so keep that all in mind when we talk about Fick's first law and Fick's second law. What are we really solving for at the end of the day? We are solving for the rate of which an ion or something or molecule will move. Either it's a gaseous species or a solid species moving through a solid. Okay. So I am going to go to Fick's second law since a lot of you had concerns about that. Okay. All right. This is the solution to Fick's second law. Basically, we're just saying we're not at steady state yet. Not enough time has gone by, and also we have an infinite solid. What that means is at this interface here, you have some concentration, okay? The CS, this concentration at the surface. And in this particular scenario, our periodic boundaries for solving the partial differential equation is that you have some concentration at the surface that's going to be constant, and you keep feeding the material, right? Your diffusive species, you keep feeding it so that your concentration at the surface is constant. So that's some CS. Your C naught is the baseline concentration in your material. So if you were a process engineer at Intel and you have a silicon wafer and your job is to diffuse and control the process where you introduce phosphorus atoms into the silicon to make it an N-type semiconductor, right? If you keep feeding that concentration where the surface is some known concentration of phosphorus, that you would use Fick's second law for. If you were a process engineer and you just introduce phosphorus and then let go, take the phosphorus source away, and then you don't do anything, you just wait until the phosphorus diffuses into the silicon wafer, you don't use Fick's second law for this because the surface concentration is not the same, right? You turn on the phosphorus source and then you shut it off and you walk away. That's not where we would use it. Where we would use Fick's second law is, let's say, carburization, the example that Janet went over, right? You have some material and you're introducing, you know, some amount of carbon into, let's say, an iron rod or something like that, and you're treating it. Okay, so we would solve Fick's second law to know over a certain amount of time t, if we want to carburize into a certain depth x, okay, how long it would take us based on the diffusivity value. And the diffusivity d would change as a function of temperature. So you've seen before that the diffusivity is temperature dependent because there's some activation energy, right? So this is just the material prefactor, this D naught. So you can calculate what D is at a certain temperature. So your diffusivity would change. So if you're talking about diffusivity of a certain material at 600 C, it won't be the same as 500 C, right? So you need to know these values at different temperatures because they also have different activation energy. Moving an ion at 600 C is not going to have the same thermal barrier as 500 C, 300 C, yada, yada, okay, at different temperatures. So when you use Fick's second law, when you have an infinite solid, you have some surface concentration that you're keeping constant, and you have this infinite supply of whatever you're trying to diffuse. That's the limit. Those are the conditions that we treat it as, right? So some semi-infinite solid. So if it's a really thin material, typically we don't use Fick's second law to solve for what the concentration is, because now you have to consider other things. You have to consider other processes like phase transformations within the thin interface and things like that. We don't really get into that in this particular class, okay? And then of course, C naught is the baseline. So if you have, let's say iron, right? And you're diffusing carbon into this iron, well, the initial concentration of carbon is what? In the solid. Rephrase, if it just has iron, what's the concentration of carbon in your iron? 0. So C naught can be 0. If you're carburizing, or if you have a carburized sample, and you already have, or if you have, let's say, a steel sample, and you already had, you know, point something weight percent of carbon in your steel already, and you're carburizing it more, then that concentration would be your starting point. Okay. So I know you all love the eutectoid phase diagram at this point, and probably, you know, breathe and live it at this point. So you probably have a feel that, yeah, sometimes it's not 0, but whatever it is, you have to know that concentration. You have to know the baseline, the C naught concentration at the beginning. And that's what you're solving for. And a lot of times what engineers are really doing is they say, okay, if I diffuse this molecule or this atom into some solid, right, then at this temperature, how much longer is it going to take me if I just reduce the temperature a little bit? Because I don't want to run my furnace at 1000 C. What if I want to save money on electricity and I don't want to run my box furnace at 1000? Can I get away with doing the carburization at 900 C, 800 C? So we're going to do an example to see how long it would take you if you just reduce the temperature by a little bit, right? How much, if you need to carburize to a certain depth with a certain concentration, if you just reduce your temperature, let's say by 100 C, how much longer is it going to take you? Because eventually you're going to have to report, or if you're the group manager, you're going to have to say, okay, you know, team, it's going to take us X times longer. There goes your weekend or whatever, you know. And so your team would probably want to know if their weekend is going to be shot, if they have to babysit this box furnace. Although in your lifetime, it will be all automated anyway, so it won't matter. Okay, so that's the 2 cents about how and when and in what circumstance would you use Fick's second law or the solution to Fick's second law. And Janet spent some time talking about the error function and why we use the error function as the analytical expression for the solution to the partial differential equation. Okay, are there any questions specifically to this? Steady state versus non-steady state, how to use the error function. Pretty comfortable with it. Have people's answer changed by a notch from not comfortable to somewhat comfortable? Okay. Okay, you're collectively, silently not agreeing with my statement. Yeah, I can do an example. I can clarify the example that Janet went through, because I think the second time around is always useful. And on top of that, I'll also show 2 other examples of how to manipulate the solution to Fick's second law in different instances when you're solving for time or you're solving for X or whatever is within the variable of the error function itself. So basically what you're saying is, okay, if I know my surface concentration CS and I know my C naught, because either I didn't start with that material diffusing or I have some way of knowing what my C naught is. Typically you're solving for what CX, some concentration at a certain depth after a certain time, right? So clearly you need to know something about the diffusivity, or possibly you're solving for the diffusivity. What it's saying here is this over some amount of time, right? If, let's say in the example, you want to solve for carburization, you're introducing carbon into something at some temperature, right? So your diffusivity will be known after some amount of time. And the question I had before was, can you reduce the temperature or can you increase the temperature, and how long is it going to take you in terms of decreasing time or increasing time, right? So what you're telling me is you still want the same CX. So your CXT, or rather maybe just your CX, because that T might change, but the concentration will be the same. So if your CS is the same and C naught is the same, you're feeding some CS, that's a constant concentration. Your C naught was what it was to begin with, right? So then if you're telling me I want the same concentration, I just want to know how much time it's going to take in terms of being shorter or longer. So what you're telling me is this is a constant, right? You're just saying, I want to carburize to the same depth and get the same concentration. I just want to decrease the temperature, or I just want to increase the temperature. What that means is this is constant. If this is constant, what it's saying to me is that this side of the equation should also be constant, right? If the left side is constant and nothing's changing, and there's an equal sign, that means the right side is constant, and thus the value should not be changing either. Knowing this will simplify your life immensely, because now you can manipulate the error function very readily without doing the interpolation and extrapolation method that Janet had shown you. What she had gone over in class with that example is just how to interpolate when you're given a data table. Now, if you had a TI something, graphing calculator that can solve for the error function, great. You don't have to do the extrapolation method. But in some particular instances, you don't even have to do that. Okay, so you asked me, what are those instances and how do I manipulate these equations? So let's get to that. And that might answer the question that Megan had. So let's see. Okay, so this was the example. I'll get back to that. I'll also get back to the Kirkendall effect after I go through some examples. Okay, so here we go. Here's the processing example. So instead of carburization, now you're putting copper into a bar of aluminum. We're assuming a semi-infinite source of aluminum, right? And copper at the initial concentration is going to be 0 because we haven't diffused any copper into aluminum just yet. Here it says it took you 10 hours at 600 C to achieve some desired CX, okay? So already you don't know what CX is, but you want to know how many hours would it take to get the same amount, so the same concentration if you lower the temperature by 100 degrees, okay? So you're going from 600 to 500. So you're given a time, you're given a temperature, and you're given some diffusivity value. So you know you're going to have to be using the diffusivity values that are given here. So just a reminder, just rewriting the solution, by the way. Right, you're saying my known concentration at the beginning in this infinite, semi-infinite slab is C naught. So that's just going to be 0, but it doesn't really matter because we don't even know what CX is anyway. And you're introducing copper at the surface, CS, and it's diffusing into aluminum. So we know that the error function solution is something like this, where if you penetrate aluminum at a certain distance X with copper, and at some temperature, 500 or 600, the corresponding diffusivity value is going to be here. And then after some time, that's your T, right? But you're telling me this is constant because you want the same CX. Now you just want to lower the temperature. Well, if this is constant, then this is constant, as we just discussed, okay? So the way around that is you can say, well, if all of that is constant, then basically X is going to be the same. Your diffusivity at 500 T, it's going to take you, 500 degrees Celsius. This should be the same. Right. You can now put, what you're saying is, if I wrote this equation right here for 500 degrees Celsius, T is going to be different for 500 degrees Celsius versus 600 degrees Celsius. Okay, it's going to take a different amount of time, but I'm trying to get to the same CX. So if CX is the same, C naught is the same, CS is the same, then the left side is constant. So what you're telling me is in your system of equations, the only thing that's changing is going to be this, right? But they should be equal to each other. So your T should be changing. Your diffusivity values are given. They're obviously different at different temperatures. And you're you're diffusing the copper into some distance x, so that's going to be the same. So essentially what's happening is you're saying, okay, what I'm really solving for is T of 500. Okay. And you know that T at 600 is 10 hours, and the diffusivity is 5.3 times 10 to the negative 13 meters squared per second. So if you rearrange this equation to solve for how long it would take you to diffuse copper into aluminum at 500 degrees Celsius, when you know it took you 10 hours at 600 degrees Celsius, so you plug in 10 hours into T600, diffusivity of 600 is given, diffusivity of 500 is also given. You're basically solving for T of 500, and that gives you, let's be a little more legible here. So what does that say to you when you drop the temperature by 100 C? It's taking you 10x to diffuse the same material into another same block of material, right? So it confirms, because you're manipulating, this similar equation, that diffusion is a thermally activated process, right? So if you increase the temperature by a little bit, by 100 C, you reduce your time by 10x. Okay, so that has significant implications when it comes to engineering design. Okay. Questions on this? Strategy. So when you're tackling a problem like this in engineering, you need to know that it's not a steady state, right? That you don't have some sort of the problem that you had before, the example of like the methylene chloride going through your gloves or something like that, right? It's not some fixed distance. Here you're solving for the same amount of copper going to aluminum distance, but the temperature is changing. So it's a non-steady state situation. Okay, let me give you another example on how to manipulate the solution to Fick's second law by using the error function, but not solving for it explicitly. Okay, so let's see. If you had something like this, where you have some sample, now we're back to carburization, and it says that your sample of steel has been carburized at 930 degrees Celsius for 10 hours, and it has reached a depth of 0.04 centimeters. Now, if you want to continue this process so that your material is carburized out to 0.08 centimeters or into your block of material by 2x, how much longer is it going to take you? Right? Clearly, it's not going to be 2x because it's not a linear process, right? So now you can manipulate the solution to Fick's second law again. So you know that here, oops. So once again, you keep on writing the solution. Right. Okay. It really wants to show you that video of the Kirkendall effect. Right, so we have that, and we're saying that our X's are changing. The depth at which we're carburizing this material is changing. So X is changing. So we're manipulating this again. Right, so X is changing, but is diffusivity going to change? No, we're at the same temperature. We're at 930 C, diffusivity is not changing, right? And why wouldn't diffusivity change? Well, yeah, right. What I was getting at is it's not changing because, right, because you're at the same temperature. This is the equation that makes my statement valid. Okay. For the most part, okay. There's always an asterisk, but for the sake of this example, diffusivity is not changing, right? And so if that's the case, then what we're really solving for is how much longer is T2 going to take you if X is going to be 2X. Okay, so if our diffusivity, we can cross out, these values are going to cancel out because they're not changing. The 2's are going to cancel out. We're solving for T2. So the amount of time, T2, which is going to be for 0.08, well, our X2 is 0.08 centimeters. And then this is going to be square root of T1, which is the square root of T1 because we're not given that yet. And the amount of the depth for the first case is 0.04 centimeters. So we're left with this analytical function where if you carburize your material and it's taking you T1 time to get to 0.04 centimeters, it's going to take you 4 times as long to get 2x of the distance in, right? So it's not a linear process. Now, I did solve for T1 because T1 was never given to us to begin with. Yeah. What's the meaning of X? So X is the depth of which you carburize it or you diffuse the material into. It's always distance? Yes. Yeah. It's always been the same. Mm-hmm. Because you're talking about something going through, you know, per time. Yeah. Oh, that was a completely different. Oh, you mean this one? Oh, this example was specific for copper going into aluminum. This is something going into steel. Oh, sorry, carbon going into steel. So it's a different example. So different case study. I could have used the same material, sure, but I just switched up the material case. Yeah. How did I get 4T? That's a great question. Oh, sorry, there should be a square here. So there's a square root. So square root of T1 was in there. So thank you for catching that typo. Because so this is square root of T1, and this is also square root of T1. So I forgot to square it when I was solving for T2. Okay. Okay, let's see if there's going to be another helpful example. Yes, there is. There might be another helpful example. So when you are solving for, let's see, where's another? Okay. If you're given an equation and you have some conditions, some known conditions, but you have some unknowns, like either your diffusivity is unknown at a second temperature, or your rate is unknown at a second temperature, or you're solving for activation energy. You obviously need to be given enough information to solve for the new condition, right? And typically that requires a system of equations. Like if you don't know the activation energy, what you could do is measure the rate of something. So in this particular example, I have rate of oxidation for a material. And the rate is just some Arrhenius type equation where you have rate times some pre-factor C, some pre-exponential, and then e to the negative q over RT. So this is something that, you know, we've been harping over and over. You've also seen it for diffusivity, where you have some pre-exponential D naught, right? So it's thermally activated. And if you're given that the oxidation rate is, you know, this value, 1.05 times 10 to the negative 8 kilograms per meters per seconds at a certain temperature, and then you're also given another rate at a different temperature, how are you going to solve for Q? Well, you're going to have to solve a system of equations, right? If you're given this, you don't know what the pre-factor is. That wasn't given. You don't know what Q is either, but you're given so 300. See, you have to convert over to Kelvin, right? So that's going to be 573K. So this is what we know so far. This is what we're given in the problem, okay? I just rewrote the rate equation with information that we know. We also know that at a different temperature, we have a different rate of oxidation. At 400. Right, so these are the knowns. The unknown is Q. So we solve the system of equations. We can say, well, if I divide these two equations by each other, I can get, so if I just divide, I get, should be +4, I think. Yep, +4. So I can get these things to cancel out pretty easily. And I can rewrite the equation so that I factor out the things that are not changing. 573. Oops, sorry. So I can get that out. So basically, I'm just dividing one equation by the other. Okay. So then I need to solve for Q. And if you have an exponential, what do? ln. Okay. So then solving for Q, you multiply the left side by 8.314, the gas constant, you move over the fractions, and you get, check your units. All right. So you can imagine if you're given the diffusivity value at one temperature, and you're solving for Q, or you're given Q, and you're solving for diffusivity at a different temperature, you would set up the system of equation in a similar fashion. What do you know, and what are you solving for? And that's it. Okay. So pretty straightforward algebra. So with the remaining time, I would like to go back just very briefly to talk about slip planes and slip directions to clarify how to solve for the angle in between two vectors. Okay. feel it. Okay, so before we go to this example, I want to go over this. Okay, so we went over how when you apply stress in a material, in a single crystal material, right, you're going to have a slip plane that's not always in the direction of the direction that you apply the stress at. So there's going to be some resolved shear stress, right? The slip plane is going to experience some amount of that stress, but perhaps not all of it, and it's going to slip in a particular direction. And we define those angles, right? We define the angle between the slip plane or the normal to the slip plane and the direction of which the tensile stress is applied as phi. And then your slip direction, the angle between that and the direction that you apply this tensile stress is going to be lambda. And so the slip direction, if you have a single crystal, and let's say you apply some stress at a certain crystallographic direction, what is going to be the angle that slip is going to be preferred at? That angle is going to be when the Schmidt factor is maximum. So cosine lambda times cosine phi is maximum. That's going to be the preferred slip direction. Okay. So that is shown. Yeah. So we worked out that, that problem. So then let's go to an example that illustrates that. Yep. All right. So here is an example. Can everybody read that? If not, I'll just read it aloud. Well, I'll read it aloud anyway so everybody can hear and follow along. Okay. So if you have this single crystal and it's oriented so that it makes an angle so that your slip plane makes a 64.4 degree angle with the tensile axis, right? So you have some single crystal and you have some slip plane like this. This is the direction of the tensile stress, and the slip plane normal phi is 64.4. So the normal, this angle right here is 64.4 degrees. And you have three possible slip directions of 30, 48, and 78. And you want to know what is the direction of the preferred slip direction of the preferred the slip. Well, you just want to know where is this going to be maximal. Right. So if phi is constant, your cosine phi is constant. What we're really looking for is then what is the value of cosine lambda? And if that's maximal, that is going to be the direction of slip. Okay. So you would have to compute what cosine of 30 is, what cosine of 48 is, degrees, cosine of 78. Okay. And if you compute that, you get so clearly this is going to be maximum. And so 30 degrees is going to be the slip direction that is most favored. Okay. And then it asks if you experience plastic deformation at 1.8 megapascal, what is the critical resolved shear stress for this material? Well, it says right here that it's going to be, well, it's going to, the slip direction is 30 degrees and phi is 64.4. So the critical resolved shear stress is going to be 0.7674 megapascal. Okay. And the last example that I want to go over before we talk about the Kirkendall effect is this example. So this example requires you to remember how to solve for angles, the angle between two vectors. Okay, so here you have a single crystal of whatever hypothetical metal, could be vibranium. I assume vibranium is a metal. It has, let's say, BCC. Sure, why not, right? Although I don't think we were ever told what the crystal structure of vibranium was anyway in the movie. And if it's oriented so that the tensile stress is applied along the 1-to-1 direction. So here, let's say you have a single crystal again. This is the direction of your tensile stress, and it is along the 1-to-1 direction. And there's slip that occurs along the 101 plane. So let's say slip occurs here. Let's say this is the 101 plane. In a direction, bar 1, 1, 1. So let's say the slip direction is bar 1, 1, 1. Okay. And we need to compute the stress at which the crystal will yield. Right? So we're solving for sigma sub y. If the critical shear stress is 2.4 megapascal. So this is what we're solving for. Okay. Well, we need to know what phi is, and we need to know what lambda is. Right? And so if you remember, generically, the way you figure out the angle between two vectors is just the dot product of the two vectors divided by the magnitude of each vector times each other. Okay. That's just generically. So you're going to apply the same methodology to phi and lambda. So if we say vector 1, right, is 1-to-1, then the components are going to be, let's say, 1, 2, 1. So second vector, let's say it's the bar 1, 1, 1 direction. So we're going to solve for lambda. Okay. So then solving for lambda is just the arc cosine of the dot product. So 1 dot r -1 plus 2 dot 1 plus 1 times 1 divided by 1 squared plus 2 squared plus 1. So you're just calculating the magnitude. So that is going to give you that. Okay. So you're just solving for the angle between these two vectors. And then similarly, if you solve for phi, what you're solving for is now so the 101 plane, the direction that's normal to that is going to be that. So that angle is going to be, so now if you know phi and lambda, you can solve for your yield by so this comes out to okay. I believe I am 30 seconds over time, so I'll see y'all next lecture. Hello.
Like obviously they don't have to add it to line.
Yeah.
In it.
Right.